Good morning, ladies and gentlemen. How are you going today? Today we're going to look at another method or technique of proofs called proof by contradiction. So this is on page 8. So the introduction to proof by contradiction is on page 8. We'll jump around in terms of examples only because it's much easier to do later. Well, it's much easier to understand the ones later on than example 17. Okay, so what is proof by contradiction? So let's just read. To prove something by contradiction, we suppose that what we want to prove is not true. The proof continues until the initial assumption is contradicted. As the initial assumption must be false, the alternative is true. So usually we use proof by contradiction with if-then statements. So the idea of proof by contradiction is, well, a statement can either be true or false. It can't be both true and false at the same time, right? So suppose like we're accusing someone of robbing a bank. So I don't know, say like, Kevin, you robbed a bank. And then Kevin's like, no, I didn't rob a bank and I can prove it to you. Well, the idea of proof by contradiction is, well, suppose the initial is false. So suppose that Kevin did rob a bank. Well, then he would need to be at the bank at the time of the robbery. But if we could have video evidence to show that he was somewhere else instead at the same time when the robbery happened, so he has an alibi, then our assumption that Kevin robbed the bank is false, which means that he didn't rob the bank because there's evidence to suggest that what we assumed is false. So essentially, the steps involved to prove by contradiction in math is the following. So we're trying to prove an if-then statement. So we're trying to prove that an if-then statement is true. Then step 1, assume the proposition to be proved is false. So we're trying to show that, well, we'll suppose that P implies Q is not true. In other words, we're trying to suppose that, remember, what's the opposite of if P then Q? Well, the opposite of if P then Q is P and not Q. So we're supposing that if P is true and Q is not true. So that's what we're supposing, assuming that it's false. We need to show that it leads to a contradiction. So we need to show that if P is true, then Q is true. And Q is true. And then we can conclude that, well, since our original assumption is false, therefore proposition is true. In other words, P implies Q is true. I mean, it feels a little bit confusing right now. So we're going to jump straight into an example to show how we can use proof by contradiction to prove a mathematical statement. So I'm going to go over and do the example on page 12 first, example 21, because it's just much easier to do. So example 21 says, prove that for every integer, so integer z, a, if a squared is even, so that's my P statement, then Q is a is even. So we're trying to prove that P implies Q for every integer a. All right? So we want to prove that for all integer a, if a squared is even, then a is even. That's our goal. Well, our technique, our trick is proof by contradiction. So write down your proof by your technique you're using. Okay, so this is the pattern, okay? So we start off proof by contradiction by supposing not. So suppose the opposite happened. Suppose not. So remember, the opposite of P implies Q is not P. Sorry, P is, let me say that again. The opposite of P implies Q is P and not Q. So we're supposing the opposite of P implies Q. So we suppose that P happens, so suppose that there is an integer a such that a squared is even, and we suppose that not q means a is not even. Okay, so remember the opposite of P implies Q is P and not Q. That's the opposite. So we're supposing that this is my P, A squared is even. This is my not Q. And you also take note that because we started off with for all integers A, we link that up with there is an integer A such that A squared is even. Okay? So the opposite of P implies Q is P and not Q, so that's what you're assuming. We want to show that eventually what we assumed at the start leads to a contradiction. So it can't be true. Whatever we assumed P and not Q cannot be true, which means whatever we assumed is false, which means our original statement must be true. Okay, so how do we do that? Right, we suppose that A is squared is even and A is not even. Well, what does it mean for A not even? Well, A not even means that A must be odd, right? Because a number is either even or odd. And we said before, if a number is odd, then it's twice the lot of some integer plus 1, where m is some integer. Because again, a number is either even or odd. If it's not a factor, if 2 is not a factor, then 1 after it is odd. We're looking at a squared in our statement, so let's square a. So a squared is 2m plus 1 all squared. So you see this all squared trick again. So a squared is 4m squared plus 4m plus 1. We claimed the opposite statement, saying that if there is an integer a, that a squared is even and a is not even, right? So if we can show that a is odd and a square is not even, then we've reached a contradiction, right? Because we suppose that a squared is even while a is not even. So if we worked with the a is not even and we somehow prove that a squared cannot be even, then we've arrived at a contradiction to this supposition of assuming the opposite statement happens. So a squared, you remember when we're trying to prove even or odd, we're trying to pull a factor of 2 out. So that leaves us with 2m squared plus 2m plus 1. So a squared equals to 2k plus 1, where k is 2m squared plus 2m, and it's an element of an integer, because if you square, multiply, or add integers, you always end up with an integer. So by definition, a squared is 2 lots of an integer plus 1. So therefore, a squared is odd. But we assumed that here we said suppose that there is an integer a such that a squared is even and a is not even. We worked with the a is not even part and we showed that, hey, look, a squared is odd. But this is not good because we're saying suppose a squared is even and then we're showing that a squared is odd. So that's a contradiction because a number can't be both even and odd. So therefore, but a squared can't be both even and odd, therefore contradiction. So supposition is false. So therefore, for every integer a, if a squared is even, then a is even. So let's recap that again, okay? So we're trying to use proof by contradiction. Usually we use proof by contradiction with if-then statements. So if P, we're trying to show if P happens, then Q happens. That's our goal. The idea of proof by contradiction is, suppose the opposite is true. So suppose P and not Q, because the opposite of if P then Q is P and not Q. So suppose the opposite is true. If we can use the opposite, the supposition, if we can somehow show that we have a contradiction, then it means whatever we assumed is false, and then a false negation means that the original statement must be true. So in this example, we wanted to show that for every integer a, if a squared is even, then a is even. So we write down what we want to show. We're going to prove this by contradiction. Or suppose not. Suppose the opposite happens. So suppose not P implies Q. What's the opposite of that? So suppose that there exists an integer a, because the opposite of for every is there exist. So for there exists an integer a, such that, because every time that there is a there exists, you have to link it with a such that P and not Q, because that's the opposite of if P then Q. So a squared is even, because that's my P statement, and it must be an and, all right? It can't be an or, so because the opposite is P and not Q. Not Q, so if Q was a is even, then not Q is a is not even. So we are using proof by contradiction. We're supposing that this is true. And then we need to use this supposition to arrive at a contradiction, a false statement. So working with what we supposed that there is an integer a, which is where a squared is even and a is not even. Well, if a is not even, it means that a is odd, because the number is either odd or even. By definition of odd, it means it's 2m plus 1 for some integer m. I want to work with a squared because in my supposition there's a statement regarding a squared. So let's work out what a squared is. Expand your bracket. I want to prove a contradiction. So if I can show that a squared is not even, then I've arrived at a contradiction, because I can't assume that a squared is even and a squared be not even as well. So to show that a squared is not even, in other words, to show that a squared is odd, we need to be able to write a squared as 2 lots some integer plus 1, because that's a definition of odd. So technically I can pull out a factor of 2, and this stuff inside is an integer, because if you multiply and add any integers, you still end up with an integer. So 2 lots of integer plus 1, where k is some integer there. So in other words, by definition of odd and even numbers, a squared is odd. But this is a contradiction because we assumed a squared is even, and we now shown that a squared is odd. So a squared can't be both even and odd. That's impossible. So it means that we have a contradiction. So what we supposed is false, which means this statement of P and not Q is a false statement. And the opposite of P and not Q, remember, is if P then Q. So therefore, that tells us that if P then Q must be a true statement, which means therefore, for every integer a, if a squared is even, then a is even. So proof by contradiction essentially follows this pattern many times. We'll do a few more so you can see what the